Okay, let me share my screen. Okay, so I chose some context about this paper. This paper has been accepted to ICLR for this year, and it's a paper on continual learning. I chose this paper because one thing I'm interested in / I want to keep up to date with in terms of machine learning is this field of continual or continuous learning. Continuous learning is when you have a model that's trained to accomplish a specific task, and then you use that model to you get new data, and you might train the model to like on that additional data to be better at the same task. Or there's a lot of different settings for continuous learning, or you might train that model on some new data to accomplish a new task. We'll go over the different settings, but it's basically this idea of like iteratively learning, training a model where you start out with some data, you train it, then you keep training it. I'm really interested in this area because I'm really interested in how it can be applied to LLMs. And when I say interested, I mean, I'm not going to be doing research on this, but I think I wouldn't be surprised if like the OpenAI and other places are doing research on this, because you know, they have this problem that they have these models that are massive, and they train it on the entire internet, but then they can only train it up to a certain point. And then they have like anything after that point is outdated. Now that creates an issue because for one, every time they want to retrain, they're going to have to train on like an increasingly larger data set. And two, it's just going to take a really long time. What if you instead could use continuous learning to just every time you get new information, like maybe once a month or once every week, you just train the model on that new information, and so your model is constantly up to date. That's one cool part of it. And the other part of it I'm interested in is like, I wonder if we could train models to actually teach themselves, or have a training process which allows the model to teach itself. These are pretty out there concepts. And the reason why I chose this paper is because I was like, I wonder what state of the art is in terms of continual learning right now. Like, how far away are we from having topics in the research in the literature that describes something like this? I would say, as it turns out, we are pretty far away from that now. But I don't, like I said, I don't exclude this from happening behind closed doors in big tech companies. Oh, and before I start on this paper, the other thing is, so besides learning to, or like a model training itself by choosing what information it trains itself on, the other element of LLMs that I think is really cool and interesting is creating like a planning process as part of their class, because we have all of this literature like chain of thought, tree of thought, things on metacognition, where if you help the model by like asking it additional questions, or asking it to separate the task into multiple components, that it does a lot better. But those processes right now are things that we have to engineer into the model, or into the process of calling an LLM. I think it would be really interesting if we could somehow find a way to incorporate that as part of the forward pass. And the only reason why I'm saying that is because this was the other paper I was thinking of presenting, which I've read before. It comes from the robotics literature, in case anyone's interested in that area or thinking about that kind of stuff. But yeah, let's move on to this paper and talk about continual learning. I think that, by the way, I think this is a great paper. This paper is really easy to read. It very explicitly points out what its findings are and explains the problem really well. It's been a while since I've read a paper that I thought was so easy to understand. So I think this is a great paper. And it's about continual learning in the presence of spurious correlations, as it says here, which basically means like learning to accomplish tasks when there might be some kind of bias in your data set. They give a really interesting bias, which I didn't know exists, but kind of makes sense in an unfortunate way, which is there's a data set of celebrities. It's called Celeb A, and it's very well known that in this data set that there's a much larger proportion of young women than old women. So there's more young female celebrities, and vice versa for men. So there's a larger proportion of old famous male celebrities to young. So, and I think that's just a bias that's created by the biases within our society for a lot of different things. But so that's an indication of bias, and that can actually create that creates a spurious correlation in the data set. So say you were trying to identify whether someone was male or female. You're training your model, or sorry, we'll do the other way around, which is what they show in figure 1. Say you were trying to classify whether someone is old or young. The model might learn that old means male and young means female, and just classify based on gender instead. I mean, sex instead. So there's a lot of so it's the model is trying to study this, and the reason why they're trying to study it is because it's a part of the problem of continuous learning that's never been studied before. I think it's interesting also because you can come up with some really interesting parallels in our own lives and how we learn about this. Like, say you learn some biased information about how the world works, then that will propagate through all of the things you learn after that, like as an assumption that you make, until something corrects that. And they're basically showing it's the same for models, that if it learns a bias at some point in its continual learning process, that it will continue to learn that. It will continue to have that bias. So let's kind of break down the considerations in a continual learning process. So the main consideration in continual learning, at least as it is formulated now, is this, it's called the stability plasticity dilemma. And that is the challenge of preventing the forgetting of previous tasks while learning new ones. So stability means that you continue to know what you already know, even when learning new things, so you don't forget about it. And plasticity is the ability to learn new things despite the fact that you have limited capacity and you already know stuff. And there's a trade-off here, because, for example, one of the naive baselines that's often used in continual learning is you would just fine-tune the model on each new task. And usually that will give you great performance on the new task that you're training it on, and then poor performance on all the tasks before it. And then the other option is to do something along the lines of like completely freezing the model, so that after a certain point, so it won't learn anything. It has zero plasticity, but it has great stability because it's going to remember everything it knew before. So that's the main, that's the main kind of consideration that you want to think about when you're thinking about continual learning. And another consideration in continual learning is this idea of knowledge transferability. They don't really touch on that here, but I think it's they mention it, and it is a really important point, which is that one of the reasons why we even care about doing continual learning is because models can learn skills from tasks that transfer to other tasks. So maybe you learn how to classify animals, and that somehow also allows you to learn how to like tell the difference between plants more easily when you're trained to do so. And that's, as they say here, that's one of the standout properties of deep neural networks. So there's some of the first models that we have that have this ability to knowledge transfer, to transfer knowledge between tasks, or continuously learn an ever-growing set of skills that can be used to perform an ever-growing set of tasks. So yeah, that's another part of the continual learning problem, but it's not really one they touch on here. They're more focused on learned biases. Let's see. I don't think I'm going to say anything else about the introduction. I think I've explained. There's one final, I'm trying to explain the key concepts. I hope that I'm not going into an unorganized fashion. There's one final key concept. So we've gone over the stability, plasticity dilemma, and then knowledge transferability. The final one is this idea of called like forward or backward transfer. So forward transfer is the knowledge learned from previous tasks is propagated through and used as part of future tasks. And then backwards transfer is maybe you learn something in the new task, and then you're tasked with accomplishing one of the old tasks. And whether you take into account that new information when you're performing that task. And you can see, if you think about it, this is an important consideration when you're thinking about learned biases. So maybe in the first task, you learn some bias, and then as you learn new tasks and then you're evaluated on them, the question is, do you continue to have that bias? Do you, or does it disappear? And vice versa. So like maybe the last task you learn some bias, and then you are asked to, like, and whether you learn, once you've learned that bias, when you're evaluated on the old tasks, you use that bias as a way to classify. So yeah, backward and forward transfer, another important concept when you're thinking about continual learning. Okay. I wanted to give an example outside of continual learning. It's the first part highlighted here about how learned biases or spurious correlations, as they're called here, can impact the model negatively. Just so it's obvious, but like just so there's like some concrete examples, because I've heard of, I'll tell the one here, and I'll tell you of a cool one that I heard about. So the example they give here is like, say you train a model to recognize birds, but all of the photos of the birds are of them flying. And then you you show the model a picture of a bird that's perching on a nest. Then there's a lot of cases where, especially deep learning models, will fail to classify it as bird because it's actually using the background as the features to classify the model instead of the animal itself. So that's an example of a spurious correlation that's created in the data set. I've heard tons of these for animals, like you have a camel camels are only in the desert, and then you show a camel in a forest or something like that, and it will tell you that it's not a camel. But one cool one I heard about when I was still studying was there was some researchers who had trained a model to classify skin cancer. So they showed all these pictures of, I think, like moles or something on the skin to the model, and they trained it, and it had like some like 92% accuracy, something crazy like that. And they published their findings. Everyone thought that we had figured out how to classify skin cancer more accurately. And then explainability techniques came out, and they did one where you, I think it was like a heat map of the image, which shows how much different pixels in the image are paid attention to. And they found out that what was actually happening is, for some reason, well, not for some reason, all the pictures of skin cancer that were shown in the data set were pre-surgery, which means that the surgeon had marked with purple marker like around the skin cancer to show that it had to be removed. So actually all the data set the model was doing was paying attention to the purple markings, and that's how it learned to classify skin cancer so accurately. So that's an example of a spurious correlation in the data set. So yeah, these things can really affect performance, and also if we trust these models that learn spurious correlations, they could have a negative impact on us as well. So it's an important problem in consideration. Okay. Yeah, we'll go through these things one by one. So one of the first things that made me think that this is a really great paper is the related work section, because I highlighted all of it because I thought it was so great such a great kind of go through of continual learning. So let's go through it kind of like piece by piece. So they say that continual learning scenarios are typically categorized into 3 categories: task incremental learning, domain incremental learning, and class incremental learning. The task incremental learning and class incremental learning assume that each task has a disjoint set of labels and the task identity is provided during training. The main difference between the two is whether the task identity is used at test time or not. So for class and for task learning and class learning, you're learning sequentially to classify like new classes, or to, I don't know, some other task, like maybe to navigate different buildings if you're a robot or something like that. But the key difference is this idea that you're told what the task is you want to accomplish at test time if you're in the task incremental learning domain, scenario, which means it's an easier version of the second one, where the model is going to have to guess at test time which one it's trying to do. It says task incremental learning adopts a structure of multi-headed networks with classification head for each task, since it uses a task identity at task time. Yep. Okay, and so there's those two, and then the third one is called domain incremental learning, and this is when the set of tasks always remains the same. So you're always trying to accomplish the same task or tasks, but only the input distribution varies as the number of tasks increases. So basically, there could be distribution shift in your data set as you get increasingly more data. So these are the 3 different types. Oops. 3 different types of continual learning. And then we go into again. So recent methods in continual learning can be classified into 3 categories. And the categories are on the different ways on how they prevent forgetting of the previously learned tasks. There's rehearsal-based, regularization-based, and parameter isolation-based methods. So regularization-based methods add regularization terms for penalizing deviation from past models, which is actually something we see in reinforcement learning and like preference learning. And balance the stability plasticity trade-off by controlling the regularization hyperparameters. So you can imagine if you had like a really high regularization hyperparameter, then you would have really good stability, but it would be hard for you to learn new things. And then there's rehearsal-based methods, which store some data points from past tasks in a small exemplary memory and replay them while learning the current task. So that would be that with each new task, you take a small part of the previous data sets and add them on. I could see that one not being super scalable, but I can also see why it's useful. And then the last one is parameter isolation methods, which allocate model parameters separately for each task by masking out previous task parameters and updating only the remaining parameters for learning a new task. It says, note that parameter isolation methods can be applied only to task incremental learning settings, since they require task identity during inference to separate parameters for each task. Yeah. Okay. And then they say, well, these are all the different methods that have been studied in continual learning, but they're limited in their use in the real world because they assume some really perfect things about the data set. The things they say that they don't usually see in these data sets are imbalanced data, noisy labels, and data set bias. And so they're saying, like, for these 3 settings, they haven't been explored yet, and we're going to explore one of them, which is the data set bias or spurious correlations. Because data set bias, I mean, every data set is biased, and that's actually what you want the model to learn. But if the bias, and if it's not biased, then you're just learning to classify randomly. But if the bias is spurious, or the correlation is spurious, then it's not a good correlation. It's a correlation that doesn't generalize. So one thing they do say here, I highlighted it in purple, and it's non sequitur to present in this paper, is they say, while 25 shares a somewhat similar motivation as ours, their overall experimental setup was not sufficiently fine-grained to fully support their own findings. It's like, this is a pretty condemning remark, even if it's a small part of this paper. They're basically saying that this paper does not have a good enough experimental setting to justify itself. It's like, wow, I can't believe they put that in there. Okay, so now they've gone over continual learning and what that is, but now they talk about like spurious correlation and deep biasing learning. So this is, how do you remove spurious correlations while you're training a model? And all of the methods, including the ones here, they rely on having a group label for your data set. So maybe your correlation is based on gender or race or something like that when you're trying to classify some property of a human. And in order to do anything to remove these biases with the methods that exist, you have to have that labeled in your data set, which is actually a very strong assumption, because how many data sets do you have that you're going to have all of your possible like spurious correlation features labeled explicitly? So I was thinking that this could be an interesting area for research, which is, how do you identify, like basically increase the number of create group labels so that you can test for spurious correlations or something like that. Which is actually something I think that like a visual transformer model could do really well for vision, and then a visual language model could do well for vision, and then probably a language model could do for text. But that's just an assumption of mine. So basically, the only thing I want to take you guys to take away from here, we don't really need to talk about the existing methods that much, but is that right now and in this paper, in order to identify and mitigate spurious correlations, you need to have a label of the variable that is like the independent variable that's causing the spurious correlation. Okay. Let's talk about the experiments. So this paper is, maybe I should have mentioned this at the beginning. This paper is completely, well, there is one technique that's suggested at the end of the paper, but I don't think they're really claiming that it's a novelty of the paper. They're just trying to create a baseline for this setting that hasn't really been studied before. So this paper is almost completely experiments. And it's just trying to study like the impact of data set bias on continual learning. So yeah, let's go through the experiments. First, notation, just so we have an idea, although I don't think this is going to be super important. But let's see. So it says each data sample in the teeth task, so like first, second, third task, consists of a tuple, xi, ai, and yi, where ai is in A and yi is in Y, where A is a group and Y is the label. So if we go all the way up to here, the group would be your sex, and then the label would be young or old. So our gender, they're saying gender here. Okay, this would be your gender, and then the label would be young or old. So you have those group labels, as we said before. And some simplifying assumptions, like they only consider a single type of bias in each of their experiments. And they consider 3 different data sets. One is called split CFAR10S, one is called Celeb A, which is the data set with celebrities, and one is called split ImageNet S. And each of these is an example of a different type of scenario for continual learning. So task IL is when you're trying to classify different classes in CFAR 10, but CFAR 100, but I guess you know which tasks you're trying to classify. I mean, which type, like which animal you're trying to, or whatever you're trying to classify. Domain IL is celeb A, so you're showing an increase. You're always trying to classify young or old, but you are given more and more data. That's celeb A. And split ImageNet 10 is class IO. So you're given new classes, and you're then at task time you aren't told which class you're trying to classify. You're just told classify this image. Now let's talk about the biases that they've put into each data set. So again, CFAR 10 is classifying like animals, objects, stuff like that. And the way that they randomly divide CFAR 10 into 10 tasks with 10 distinct classes, and what they do is they add like a bias themselves. So this is a synthetic data set. They say, given a skew ratio of A greater than 0.5, half of the classes in each task are skewed towards the grayscale group and the other half towards the color group. So they're changing the coloring on the images so that like 50% of the tasks, I mean the images have that like a specific coloring, and the other one have a different coloring. But then at test time, they're going to show all the images without this skew. And then in celeb A, it's the one that we talked about, where there's already a bias in the data set between gender and age, essentially, and they can control that because they know they have labels of when someone's old or young, so they can, and male or female, and so they control that bias. And then for split ImageNet 10, I do forget. This one I didn't exactly understand, but basically they add a watermark to the images. And because they say over here, I'll just read it out, and if anyone has any comments or questions. It says, it is widely known that deep neural networks trained from ImageNet are biased towards watermark. Namely, the ImageNet pre-trained models predict an image as the carton class when injecting a watermark to it, since most of the carton images in the ImageNet training dataset include the watermark. So I guess they're considering the watermark bias. So basically the bias here is that models that are cartons have a watermark on it, and they can inject this watermark easily into other images. So those are the three biases. Yeah, and then they have two like very simple baselines. One is the one I said, where you fine-tune the model on the newest task. And then the other one is called model freezing, where you freeze the model parameters from the previous task, and I guess you don't even train on the new task. Or maybe you train very few models. And then they have a number of different continual learning techniques for the three different categories that we talked about before. And they can control like the stability plasticity trade-off by tuning the hyperparameters of each technique. When do they use this? And they use a debiasing technique called group DRO, although I don't think that, okay, maybe they do. I didn't realize that they were using that as part of the experiments. My bad. It doesn't really matter, in my opinion, understanding this so much, because like I said, one of the great things about this paper is they very, very explicitly say the results, which is what I liked about it, because we'll go through the metrics now, but I did feel like I'd have to think maybe for an hour or two about these metrics to really understand them and possibly try to implement them. So there's two metrics that they use, or actually three, but two of the three are measuring the same thing, because you'll see why. So the first metric is called normalized F minus I. which is the relative weight on plasticity and stability. So F, if I remember correctly, is, okay, let's go through it. In equation 1, A is test time accuracy. DJ is like a specific data set, but it really means task J. And so this is saying, let's see. So this is measuring stability. Great. So this is saying, what is this saying? This is telling you the difference in test set accuracy between HL, which is your best performing model, and your current model. So, okay, so this one is saying, like, what's the difference in test time accuracy for each of the previous tasks between the best model of the previously trained models and your current model, which is HT. So this is a measure of stability because, like, the larger this number is, or actually, sorry, the smaller, the more negative this number, smaller this is? No, the larger this is, so the larger the difference in test time accuracy, the worse that your model performs, essentially. And then, and that's because that means that, like, your current model has a lower test time accuracy on all the previous tasks than the best performing model so far. And then the IT is measuring plasticity because it's saying, okay, probably the best model for learn the current task. So the most plastic model, if that's a correct term, is one that's just fine-tuned on the current task. And so what's the difference in test time accuracy on the current task of like versus like a model that's been trained on this task with continual learning methods? And basically they normalize the difference between these two, and they say over here, the normalized F minus I indicates the model focuses more on stability as the value becomes lower and more on plasticity as it becomes higher. So the higher this number is, the more the model is able to learn new things. The lower it is, the more the model is able to remember the things that it already learned. And then they have a metric that measures the amount of learned bias in the model, and that is it's called the bias flipped misclassification rate. And so if I remember correctly, it's when you take, so basically you take a data point that doesn't include this bias and isn't the class that the dataset biases it towards. So for example, in Celeb A, it would be an old female celebrity. That would be an example of a bias flipped misclassification. And you see how good the model is at classifying, essentially. But one thing that they do here is this BMR, it actually takes data points. It would be like, okay, let's take an old male photo and make that into an old female photo, which you can't really do easily unless you use a really good generative model. So they were able to use this BMR on 2 of the data sets, but they weren't able to use it on Celeb A, because as I say, it might be challenging to generate bias flip samples, such as transforming a woman image to look like a man. And for that, they use another metric, which they call difference of class-wise accuracy, which is what I just described before, where you just take examples of where the bias, like the rare examples where the bias doesn't exist, and you test how accurate you are on those, at classifying those. And like it says further, just so further note that high BMR or DCA corresponds to the model possessing larger bias. So here, like, higher means more bias. It's good to know. Okay. So for experiments, they try to figure out the impact in terms of forward transfer and backward transfer. And the way they do that is they create a continual learning task with 2 tasks in it. So you have your first task and your second. To measure forward transfer, they introduce varying degrees of bias into the earlier task, and then test how much bias exists in the later task. And then for backwards transfer, they introduce bias into the latter task, the second task, and they test how much the bias is incorporated into the model when performing the first task. I'm not actually going to go. Like, these graphs are cool, but they're kind of confusing because you've got a lot of results on them. And so I'm just going to go through the key results because they state them very clearly, which I like. So the first result that they have is about the forward transfer of bias, which is namely, these results clearly demonstrate that continual learning methods promote the forward transfer of bias because they tend to remember the knowledge of past tasks, even if it contains some bias features. And I think they say a little bit. I don't know where they say it, but I'm sure they say it. So they basically say that, if you have a model that is focusing on stability here, you'd assume that the bias transfer is greater, which means that, because if the first task is the model, the task the model learns first, and it's a very stable model, it's going to learn more, keep that bias, even if the second task doesn't have it more. So in terms of forward transfer, having a stable model actually increases forward bias when you're learning it. And then in terms of backwards bias, it's what we said before. This means that the more continual learning methods prioritize plasticity over stability, the more the bias obtained from T2 is transferred to T1, i.e. backwards transfer of bias occurs more. What's interesting here, I think, is that we have this dilemma in continual learning of stability versus bias, and you can't win either way, because if you know that you're only going to use the model on future tasks, then maybe you want to I don't even know. Yeah, basically, if you prioritize stability, then you're going to be bad at forward transfer. You could easily transfer bias forward, and if you promote plasticity, then you could easily transfer bias backwards. So there's really not a winning scenario here. They said something here that I highlighted in purple because I didn't understand it. Okay, so as a straightforward solution to backward transfer of bias, one may naively consider applying an existing debiasing technique to model the obtained after learning. However, we can easily expect the accuracy of the previous testing bias. Okay, so basically they're saying over here, after they've shown that the bias is propagated in both directions, that if you use existing debiasing technique, it will reduce the bias in the current task, but at the expense of the accuracy in the previous tasks. And they have some results in the appendix for this. Okay. So they've shown, just in terms of performance on the task metrics, that the bias exists. And then over here, what they show is that they show that the bias exists also in the feature representations that are used for classification. Let's see. Actually, I'm not going to go through that, but it's just they can also tell when looking at the second to last feature layer. So the second to last hidden layers representations, they can see the bias in those as well. Okay, then they test continual learning with a longer sequence of tasks. So far they've only looked at the case where continual learning has 2 tasks in sequence, but probably more realistic continual learning will have more than 2 tasks, or could have many tasks. Depending on who knows, maybe we'll have models that are trained over hundreds of years with continual learning. It could have thousands or millions of tasks. That would be cool. But so when they do experiments where they introduce bias in like different parts of different tasks in the sequence, and they do it with 10 tasks, they say, we emphasize that from figure 5a, the color bias of T1 can persist even if, so the bias can persist even if a CL model learns it. The additional 9 tasks that have 0 bias. So even if one task, and it says when focusing on stability, even if the first task is the only one that contains bias and we train it with 9 more tasks, could still contain that bias if we're focused on stability. So, then they show over here that you can accumulate bias as well. So if multiple of the tasks contain that same bias, then it can accumulate and get worse. Then they show that if you have 2 different types of biases in the data, that the model can learn both of them. I mean, I think a lot of these are obvious once you show that the bias can be learned and then propagate, but it's still good to show. And then they propose a technique as a baseline for this setting. So it's a technique where, say we know that there's biases in the data set and that they hurt the performance of the model. So they're spurious correlations. They hurt the generalization ability of the model. What could we do? And so they combine 2 techniques to do this. One is called GDUM, greedy sampler and dumb learner, and the other one is called deep feature reweighting. So GDUM greedily stores a small number of data into an exemplar memory equally for each class and all tasks, and uses them to train a model from scratch during the test time. And then deep feature reweighting retrains only the classification head using a small number of group balanced data from training a model from scratch using an entire training data set that may contain any data set bias. So what they do is they suggest a method which first during a continual learning using like a classic technique, they store group class balanced data over all the classes and groups in a greedy manner. So they create a small data set that has balanced classes with respect to the groups that might be create bias. And then right before test time, they retrain the classification head, so like the last layer essentially of the neural network, using this balanced data set. Yeah, again, I don't feel like they're really claiming any kind of like that this is a groundbreaking technique. They're just trying to create a baseline for this problem. And what they're able to show on split CFAR10 is that actually using their method, they get both better accuracy and lower bias for any technique that you use it for versus not using it, and also better than like these 2 methods just by themselves. And then actually for Celeb A, they got worse accuracy in each case, but they did get lower bias. So they sacrifice a bit in terms of accuracy. So you could see here, like it went from 80.99 to 80.19, but you get lower bias by a couple of percentage points. So, oh, sorry. This is the method that they're suggesting, just like create a small data set that's balanced, train it right before test time, and then evaluate the model. So yeah, that's the paper. Hope I didn't go through it too quickly. Like I said, it's mainly experimental results, and it's focusing on the specific problem of spurious correlations in your data set. Definitely an interesting consideration. I guess they kind of label it, they talk about it here. Like the things that we haven't considered yet, which should be considered, are imbalanced data sets, noisy labels, and data set bias. I feel like these are very machine learning terms. It would be interesting to ask someone, maybe with a psychology background, like what kind of biases do we learn in our lives and maybe see if we could come up with I think there's probably a larger set of things that might need to be considered for continual learning. But yeah, that's the paper. Do you guys have any questions or things you want to ask or talk about? Okay. Well, if not, thanks for coming. Oh yeah, go ahead, Jane.
Yeah, I've got one comment, and that is a paper that I read a while back. And what they're doing is they're looking at learning in mice, I think it was, and they were looking at the reinforcement learning actually in cells in the brain as to when the expected reward was not actually the magnitude that they expected. And so this is in live mice, and they started then shining a light, then ringing the bell, then delivering the food. This isn't exactly correct, but the setup is kind of like this. Then once they'd learned that, they were going to get a big gaseous windows. They started removing the bell or that symbol. But the similarity to this is that the mice failed to learn the fact that the light was a precursor. So the domain had shifted from essentially there was a light, there's a bowel, there's food. The animals learned bowel food, moved the bowel. They failed to learn the fact that the light was a precursor as well. But also the temporality of that is similar to continual learning. Like, so what elements are good as new data is coming along into our large language model? What can you rely on? What parts do you need to throw away? It's very hard problem, as you say. I'm going to dig into the done, more, because I like that.
A very hard problem. That's interesting. I wonder if it means that like mice have short attention spans or something like that.
Yeah, I don't know.
One question from the chat is, what is the realistic application of this paper in the context of LLMs? Wouldn't it be impossible to make use of continual learning in this context, given that most of the data contains some form of context? And if so, is there a method of automatically labeling different types of correlation/bias types? To answer your last question first, I'm sure that there are methods for automatically labeling correlation and bias type, because I'm sure that they're learned to make safe LLMs. How accurate they are is another story, but there's a huge amount of literature on identifying bias with LLMs. I actually don't think you could which is something you're pointing out. I don't think you could easily use this paper in the context of LLMs, but it's also just pointing out a result. It's more like a consideration. It doesn't really provide a solution. It's saying if you are training a model in the continual learning setting, you have to be wary of bias because it does propagate. And so I think a follow-up paper might be the one that could be applicable, but you'd have to solve the point that you're talking about, which is automatically labeling and then identifying that bias somehow. Because without that, most of the literature on continual learning so far, or actually this is the first paper on it, but like this type of work wouldn't be applicable. Okay, so I think there aren't any more questions. And if that's the case, thanks everyone for coming. Hopefully we'll see you here next week. I think Vahan's presenting. I'm not sure.
No, it's Ben. I'm the big
Ben is presenting. Okay, Ben's presenting a really cool paper on, I think, generative networks for graphs, which is nice. I'm excited to learn about it. And have a good weekend. Thanks. Bye.
Thanks, Peter.
Thank you.